All right, so far we have seen external interrupts and timer zero overflow and timer CTC mode, timer zero CTC mode. Now, from the interrupt vector table, you can easily see that we have got lots of different interrupts over here. Now, how does AVR prioritize these interrupts? So which one to serve first if you have multiple interrupts enabled? Now, this is actually related with the address of the interrupt in the interrupt vector table. And the lower address has got the highest priority. So the reset has got the highest priority than the external interrupts, then timer 2, timer 1, timer 0, SPI, user, ADC, timer 1, compare image, and so on. Okay, so the highest priority, the ones with the lower address, and the lowest priority with the highest address. Okay, be careful over here. If you are going to use multiple interrupts, you have to make sure that you are actually running the or executing the right interrupt. So another thing that we need to consider when we are considering multitasking, if we enable multiple interrupts, what do we need to do? How are we going to do that? Now, in AVR, as we are using the status register I bit, which is the most significant bit as the global interrupt enable, whenever we get into the ISR, this enable is going to be low. Okay, so you are not expecting any other interrupt. But what you need to do is you have, and that I bit is going to be re-enabled when red I is coming in. Now, if you want to create nested interrupts or interrupt in an interrupt, while you are serving that interrupt in the ISR, you have to be re-enabling, you have to re-enable that I bit, okay, before the red I, so that while you are serving an interrupt, that means you can expect a new interrupt. Now, the priority by the interrupts is coming from the vector table again. The lowest address has got the highest priority. So for example, if you are running, let's say, timer 1 interrupt routine, and then the external interrupt comes in, the timer 1 interrupt service routine will stop. It will serve the highest priority external interrupt. When this is done, it will return back to timer 1 and finishes that interrupt. Okay, so the interrupts works with their priorities, and if you are creating nested interrupts, again, the prioritized one has got the control. Now, we need to be careful over here because you might need to save the context of your registers, because as you are running ISR and if you are running nested interrupts, and if you are using the same registers in both of them, you might need to save the content of those registers into the stack by using pushes and pops. And also the state of the previous interrupt trigger. So if an external pin active low interrupt triggered execution of ISR, enabling interrupts within an ISR too early may cause the same ISR to be re-entered infinitely. Okay, that means a stack overflow. So you have to be careful when you need to call that interrupt, otherwise it will just be an infinite loop. So here's an example. It's asking for if that program is going to work. Now, when you look at it carefully over here, there's nothing on this side. The only problem is over here. So you use R20, we set DDRC to be an input, then DDRD be an output, then you send the value to port C, okay? And we increment R20. Now we increment R20, we have a value in R20. Now what we do is R20 is 1. And then suddenly interrupt comes in with the timer. Now what will happen is pin D value will be stored in R20. Now you have got 1 over here, but the R20 now will have the value of pin D, and that will be incremented. So this program is not going to work properly because R20 is shared between the ISR and the main routine, and it's overwritten by pin D. So you send out that one, and when you return back from interrupt, it will return back over here, and you have the value of pin D. You don't have this 1 over here anymore. So using of the same registers creates a resource conflict, and the value of R20 in the here loop will be corrupted on interrupt. So how do we fix this? Either we use, if we are not desperate about the registers, we can use different registers, which is the easiest one. Or what we can do is we can save the context, the data in R20 before we serve any of the ISR by pushing R20 into the stack, serve the ISR, then pop R20 back from the stack to the register, and when the red eye comes in, you go back over here and you have got the original value. Okay, so if you run out of the registers and you're desperate about the registers, you can use push and pop routines in order to save the value of that register. So when we are running ISRs, we might also need to save the SREG because the flags are changing, and you might need to hold the value of the ISR SREG. So you have to use push and pop before you get into the ISR service routine. At the beginning, you just save the context into stack, and then once you are done with the ISR, you can use pop R20 and you can restore the value of R20 from the stack. So in this case, the status register conditions do not change in the program that was interrupted. Okay, so we can carry on servicing before the interrupt, whatever we were serving. Okay, so we have done an example using assembly. We can also do an example using C, and for each compilers or different assemblers, they require different C codes actually. They have got the machine specific instructions for handling interrupts. So for example, in this one, timer 0 to generate square wave on pin B, port B5, while at the same time transferring data. So this is a similar example that we have done. And you can see the differences over here. In WinAVR, you have to use AVR IO.h, but micro C, this is AVR interrupt.h. And you can just say, okay, DDRB is going to be an output, bit 5, TCNT minus 32, because we are doing it for 4 microseconds, and TCCR is 1, no prescaler, normal mode. We enable the timer overflow 0 interrupt enable. We enable the global interrupts, okay? And in micro C Pro, you have to use this command, sreg ibit 1, that's the difference. And DDRC 0 and DDRD is F, so inputs and the outputs. Then the value of pin C will be assigned to port D. And the interrupt vector, this is for Microchip Studio. You can just say ISR timer 0 overflow vector, and you just toggle the port B. Okay, so this is specific to the assembler or the environment that we are using. And we also have the vector table in order to set up a ISR vector table. So in Microchip Studio, You can just say start typing ISR and the timer if you remember the name a little bit. If not, you may refer to the AVR manual and you can find the exact name of it. You can look for from the link as well. Or you may reach the symbolic interrupt name list for interrupt vector table by typing IVT, and you can find out the Micro C Pro AVR code editor and control space to get help from the code assistant. So these are all the possibilities if you are going to use a C programming. And let's do an example. Use timer 1 and CTC mode to write a program that toggles pin port B5 every second, while at the same time transferring data from port C to port D. So it's again the similar stuff, but we are going to use timer 1, and we have got 8 megahertz clock. So let's do the calculations first, and then we can do the rest. We are looking for every second. So the prescaler, we need to use a prescaler because we have got 8 megahertz clock. I'm just going to do it quickly. You can look for the timer references. If we use prescaler 124, so this is going to be 1 over 8 megahertz times 124, which is going to give us 128 microseconds. So 1 second divided by 128 microsecond, it will give us the value of 7812. So if we are using CTC mode, that means OCR 1A, let's say, it's going to be 7811 because it has to start from 0 to 7811 for this value. Or you can just say hex value 0 hex 1E83, both acceptable. Now, if we are using a prescaler, that means the clock select has to be 124, which is 101. Okay, so maybe we can drop those down. So we have to use 101 for the prescaler. And CTC mode is 0100 for the VGM for TCCR 1A and 1B has to be configured. So we have to set them down. TCCR 1A and TCCR 1B. So nothing will be different over here. Only difference is this has to be based on CTC, so 0100. So these are 00. So that means 0 hex 00. And 1B, it has to be 2, has to be 1, and 3 has to be 0. So 000 up until there. And then we have got 1, and the clock select is 101. So that's going to be 1101. So 1101, it's going to be D. Okay, so we can get that. That will be 0D, and that will be 00. So OCR1A will be 1E, the high byte and the low byte. So that has to be configured. And we don't need to configure anything else. The ports needs to be configured. and we just need to toggle it. Okay, so let's write the code for it. Let's erase this one. So void main now ddrb hex 20. So ddrb bit 5 is going to be an output. Then TCCR1A, which we have already defined it, calculated as 0 hex 00. And TCCR1B, it's going to be 0 hex 0D, which we have calculated that for prescaler 124 and CTC mode. Then OCR1A high byte, it's going to be 0 hex 1E. So high byte of OCR. OCR1A low byte, it's going to be 0 hex 83. Low byte of OCR. So the timer is set. We have to set the timer interrupt for timer 1, which is 1. It's CTC mode, so OC output compare interrupt enable 1A has to be set. Enable timer 1 compare match. Then of course we need to enable the interrupt, so I can use sreg or the same as this one. We can use SEI. Let's use it that one. So the global interrupt enable. So assuming Microchip Studio is used. And then DDRC is going to be 0 hex 00, which is going to be port C as an input, and DDR 0 hex FF port D as an output. And while we are running ordinary routine, just copy the contents of port C to port D. So this is our main, and in the ISR, so ISR timer 1, we can look for it. ISR timer 1, compare A. A is the routine that we need to use. Okay, and in that routine, what we need to do is we just need to toggle port B. So port B, hex 20. So toggle port B 5, and that's it. You don't need to do anything else. So you can use it either timer 1 compare ISR, IV, IVT address timer 1, this bit, and you can use SREG IBIT for interrupt enable, and you can just toggle the clock. So microchip or AVR Pro, you just need to be careful which one to use. And the last one, assume that the interrupt 0 pin is connected to a switch that is normally high. Write a program that toggles port C pin 3 whenever interrupt 0 pin goes low. Use external interrupt in level trigger mode. So we are going to use external interrupt 0 pin, and we have to set toggle port C pin 3 whenever interrupt pin 0. So in ISR, we have to toggle port C bit 3. Okay, and when it goes low, actually, so that means it's going to be a falling edge. Okay, so DDRC bit 3, it's going to be set as output. Port D, it's pull-up activated because this is in port D, and we have to enable the registers, external interrupt enable register for interrupt 0. You don't need to set anything for the control register A, default value for it. Enable the global interrupt enables and wait over there. Whenever the button is pressed, all we just need to do is, because this is low, that's why it's 0. All we just need to do is we just need to toggle it. Okay, so that's all I want to say about the interrupts. I think they are pretty straightforward. You just need to know which interrupt vector you need to use depending on the hardware resource that you have. And you have to make sure that you enable the interrupt, and you have to enable the global interrupt enable as well. And then rest is just the similar what we have done it before. So please do study, and if you have any questions, feel free to ask them. Thank you.